Hello there, and welcome to the Sleepy Space Channel. Within 1 light year of Earth, there are roughly 1 trillion objects, and we have never seen a single one of them. The familiar solar system, every planet, every moon, every asteroid ever catalogued, occupies about 1/10 billionth of that volume, and everything past it is known only by inference. A shell of frozen bodies sitting 3 degrees above absolute zero, drifting at the speed of a car. A fog of interstellar hydrogen that outweighs every comet in that shell by 100-fold. An invisible halo of matter roughly matching all the planets combined, passing through you as you lie there. Of the entire sphere, we have detected anything at all in about 4 parts in 1 billion of it. Tonight we count what is out there, shell by shell, from the ground beneath you to a boundary that light needs a full year to reach. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to hold. The distances are patient, and they have been for a very long time. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Tonight we are going to count something. Not explore it, not travel through it, not imagine what it might feel like to stand somewhere far away. We are going to take the space immediately around us, draw a boundary at 1 light year in every direction, and make an honest inventory of everything inside it. This is a census. It has a beginning, a method, and an answer, and the answer is stranger than the question suggests. The first thing to understand is the size of the region we have just enclosed. 1 light year is the distance light travels in a single year, moving at 300,000 kilometers every second, without pause, without slowing, for 12 months. That comes to about 9.5 trillion kilometers. In miles, it is about 5.9 trillion. Neither of those numbers means anything to a human being. They are simply long strings of digits that the mind refuses to convert into a feeling. So it is better to measure the sphere in a unit we already have some relationship with. The distance from the Earth to the Sun is called an astronomical unit. It is about 150 million kilometers, and light crosses it in 8 minutes and 20 seconds. Every morning, the light that reaches your window left the sun 8 minutes earlier. That is 1 astronomical unit. 1 light year is 63,241 astronomical units. That number deserves a moment of stillness. The gap between the Earth and the Sun, the gap that takes light more than 8 minutes to cross, the gap that defines the seasons and the year, and the entire scale of ordinary daylight, fits into tonight's sphere 63,000 times over. And that is only the radius. The volume grows as the cube of the radius, which means the sphere we have just drawn contains something on the order of 3.5 billion trillion cubic kilometers of space. There is no honest way to picture that. But there is an honest way to compare it, and the comparison is the reason this episode exists. Shrink the whole thing down. Let the distance from the Earth to the Sun become a single centimeter, roughly the width of a fingernail. On that scale, the orbit of Neptune, the outermost of the planets, is a circle about 30 centimeters across. You could draw it on a sheet of paper. On that same scale, the edge of tonight's sphere lies 632 meters away, more than half a kilometer. The entire planetary system, everything you have ever seen photographed, everything that appears on the diagram in a classroom, is a hand-sized ring at the center of a sphere more than a kilometer wide. Put another way, and this is the number that governs everything that follows. Everything inside the orbit of Neptune occupies about 1/10 billionth of the volume we have just enclosed. Not 1%. Not 1,000th. 1/10 billionth. The familiar solar system is not the contents of this sphere. It is a speck at the middle of it. There is a second thing worth saying about the boundary, and it is that the boundary is not real. A light year is a unit of time wearing the costume of a unit of distance. It is defined by how far light gets in one orbit of the Earth around the Sun, which is a period set entirely by the size of one small planet's path around one ordinary star. Nothing in nature marks that surface. If you were somehow carried out to it, you would find no membrane, no change in temperature, no shift in the darkness, no sense of having crossed anything at all. There is no fence. There has never been a fence. This matters more than it might seem, because the solar system has at least 3 plausible edges, and not one of them sits at a light year. The first is the heliopause. This is the place where the Sun's outflowing wind of charged particles is finally stopped by the pressure of the gas between the stars. It lies at roughly 120 astronomical units. That is about 1/500th of the way to the edge of tonight's sphere. If the heliopause were the edge of the solar system, then the solar system would occupy roughly 100 millionth of the volume we are counting. The second edge is gravitational. The Sun's pull weakens with distance but never stops, and it competes with the smoothed pull of the rest of the galaxy. The place where the galaxy finally wins lies somewhere between 1 and 2 light years out. Tonight's sphere sits comfortably inside that domain. Everything we are about to count is still, in the strict sense, the Sun's property. The third edge is made of comets, and this is the one that matters most. The outermost shell of icy bodies bound to the Sun extends to perhaps 100,000 astronomical units, and possibly further. 1 light year at 63,000 astronomical units does not sit outside that shell. It sits inside it, roughly 2/3 of the way through. Our boundary cuts straight through the middle of the Sun's own outer territory. So the sphere is not a container. It is a cross-section. We have taken a slice through something that continues past the cut, and we are going to inventory the slice. There is one sense in which the boundary is genuinely real, and it is a boundary in time rather than in space. Anything happening at the edge of this sphere tonight will not be knowable here for a full year. The surface we have drawn is the set of all places whose present moment we will learn about 12 months from now. Everything inside it is closer to the present than that. Everything outside it is further away in time. In that sense, the sphere is not an object at all. It is a shell of delay, expanding outward at the speed of light, and you are sitting at the exact center of it. Consider what that means for the ordinary business of looking up. When you look at the moon, you are seeing it as it was a little over a second ago. When you look at the Sun, you are seeing 8 minutes into the past. Jupiter is roughly 43 minutes behind. Neptune is 4 hours behind. And then, past Neptune, the delay stretches by an enormous factor. 4 hours takes you to the last planet. A full year takes you to the edge of the region we are counting. That ratio, 4 hours against 12 months, is perhaps the cleanest way to feel how much of this sphere lies past everything we normally think of as the solar system. The sphere is also not sitting still. The Sun is moving through the galaxy at about 230 kilometers every second, dragging this entire volume along with it. In the time it takes light to cross the sphere's radius, the Sun has traveled about 7 billion kilometers. The region we are counting is not a fixed piece of space. It is a moving bubble, sweeping steadily through the galaxy, carrying its contents with it and constantly exchanging the space it happens to be passing through. And the sphere is not symmetrical in any physical sense. The bubble the sun blows has a blunt nose in the direction of travel and a long trailing tail behind it. The comet shell is thought to be flattened in its inner parts and only properly round further out. The interstellar material we are moving through varies in density from one region to the next. The perfect sphere is a convenience of the counting, nothing more. What we have then is a volume of space defined by a human unit, containing a solar system that occupies a 10 billionth of it, cutting through a comet cloud that extends past it, moving through the galaxy at 230 kilometers a second, and holding within its surface everything whose present we could possibly learn about within a year. Now we can begin the count. We will work outward, shell by shell, from the innermost region to the boundary. And alongside the census, we are going to keep a second list running in parallel. For everything we count, we will also record something simpler and much more uncomfortable. Of all of this, we will note how much has ever actually been seen. The census begins at the center, with the only object inside the sphere that makes its own light. The Sun holds about 99.86% of all the mass in the solar system. Everything else divides the remaining 0.14% between them. Every planet, every moon, every asteroid, every comet, every grain of dust that has ever been counted, all of it together amounts to less than 1/6% of what the Sun weighs. And of that small remainder, Jupiter alone takes roughly 2/3. The honest summary of the solar system's mass is a star, then Jupiter, then a set of rounding errors. It is worth putting real numbers on the planets because one of those numbers is going to come back later in a way that is genuinely surprising. Measured in Earth masses, Jupiter is about 318. Saturn is about 95. Neptune is about 17. Uranus is about 14.5. Earth, by definition, is 1. Venus is about 8/10. Mars is a little over 1/10. Mercury is about 5/100. Added together, the 8 planets come to roughly 446 Earth masses. Hold that number somewhere at the back of the mind. Something invisible is going to match it before the night is over. The moons are a smaller story than most people expect. Somewhere over 300 are now catalogued, and the number climbs every year as instruments improve around the giant planets. The largest of them, the great icy and rocky worlds circling Jupiter and Saturn, each come to about 2/100ths of an Earth mass. Add every moon in the solar system together, and the total is roughly 1/8 of a single Earth mass. 300 worlds, several of them larger than the planet Mercury, and collectively they do not amount to 1/8 of the ground beneath you. Most of those moons are not the great round worlds that appear in photographs. More than 200 of the catalogued satellites orbit the 2 largest planets, and the majority of them are irregular lumps a few kilometers across. They were not formed in place. They were captured, drawn in from passing populations early in the system's history, and their orbits show it. Many are steeply tilted. A great many travel backwards, circling their planet in the opposite direction to the planet's own spin, which is a signature that no object formed in a flat disk around that planet could produce. They are trophies rather than children. The Sun, meanwhile, is not a fixed quantity either. It converts about 4 million tons of its own mass into light every second, and it has been doing so for 4.5 billion years. Over that time, it has shed something on the order of the mass of Saturn purely as sunlight. That loss is continuous, and a portion of it is passing through the room you are in right now. It is also the reason the whole system is very slowly loosening. As the Sun sheds mass, its grip weakens fractionally, and every orbit in the system creeps outward by a tiny amount each year. Another scale model helps here, because the planetary system is difficult to hold in the mind at true proportions. Let the Sun be a sphere 2 meters across, about the height of a person. On that scale, the Earth is a grape, 18 meters away. Jupiter is a grapefruit at about 95 meters. Neptune is a plum at roughly 540 meters. And on that same scale, the boundary of tonight's sphere would lie more than 1,000 kilometers from the 2-meter Sun. The planets are all within walking distance of each other. The edge of the census is on the other side of a continent. There is a demonstration that gets repeated often because the result is so hard to believe. If you lined up all 8 planets side by side, edge to edge, the whole row would fit into the gap between the Earth and the Moon, with room left over. That gap is a distance light crosses in a little over a second. Everything with a name and a surface in this system fits inside 1 light second, laid end to end, and we are counting a sphere with a radius of 1 light year. There is something quietly pleasing about the arithmetic here. The Sun is a furnace of unimaginable size, and around it, the entire accumulated inventory of solid ground and liquid ocean and frozen ice in this system is a handful of crumbs. Everything that has ever been walked on, landed on, dug into, or photographed from orbit is 1 part in 600 of the Sun's weight. Now the second list, which records how much of this innermost region we have actually seen. Here the answer is genuinely good, and it deserves to be said with something like warmth rather than apology. Every planet in the solar system has been visited by a machine sent from Earth. Every one of them has been photographed from close range. Several have been landed on. 2 have had wheeled vehicles driven across their surfaces for years at a time. The surfaces of the rocky worlds have been mapped at a resolution finer than a city block. The atmospheres of the giant planets have been sampled directly by probes dropped into them, transmitting data as they fell and as the pressure closed around them. This is a real achievement, and it happened within a single human lifetime. The generation now alive is the first in the history of the species that has seen the surface of every planet in its own system. Before that, for every other generation that ever existed, the planets were points of light that moved. And yet even here, in the best observed part of the entire sphere, the seeing is incomplete in ways that are easy to overlook. The flaws of certain craters at the poles of the innermost planet and at the poles of our own moon have never been directly imaged in visible light. This is not a failure of instruments. It is because no sunlight has fallen into them for something on the order of billions of years. The axis of those worlds is tilted so little that the Sun never rises above the crater rim. The floor sits in permanent darkness, at temperatures below -200 degrees, and the only way anything has been learned about it is by bouncing radar into the shadow or by measuring the neutrons that come back out. The surface of the second planet has never been photographed for longer than about 2 hours at a stretch. The atmosphere there is so heavy and so hot that every machine which has ever landed was destroyed within a couple of hours of arriving. What exists of that surface, from direct observation, is a small number of photographs taken by machines that were already dying as they took them. Everything else is radar, mapped through the cloud from orbit, which shows shape but no color and no texture. The interiors of the ice giants remain inferred rather than observed. Nothing has ever descended into them. The physical state of the material beneath their atmospheres, whether it behaves as a fluid or as something stranger, is worked out from the way their gravity fields are shaped and the way their magnetic fields behave. Both of those magnetic fields are tilted and offset in ways that no complete model yet explains. And beneath the ice shells of several outer moons, there are almost certainly oceans of liquid water, kept warm by the flexing of tides rather than by sunlight. One of them may contain more liquid water than every ocean on Earth combined. Nothing has ever touched that water. Nothing has ever seen it. Its existence is inferred from magnetic induction, from the way the surface ice has cracked and reformed, and from plumes of vapor that vent through the shell and freeze on the way out. So even in the innermost region, where the record is strongest, there is a long list of things that remain closed. But the record is strong, and it would be dishonest to describe it any other way. This shell of the sphere has been examined about as thoroughly as physical distance allows. And here is where the parallel list turns. Everything just described, every planet, every moon, every landing, every mapped surface, every dropped probe, fits inside a sphere, 30 astronomical units in radius. The whole of it. All 8 planets, all 300 moons, every mission ever flown to any of them. 30 astronomical units, against a boundary at 63,241. The volume ratio, as we said, is about 1/10 billionth. Take that seriously for a moment. If you were to represent tonight's sphere as a room, the entire well-observed solar system would not be a piece of furniture in that room. It would not be a coin on the floor. It would be a speck of dust too small to notice on the surface of that coin. And it is the only part of the sphere where the observational record is anything better than fragmentary. Everything from here outward gets emptier, colder, slower, and very much less observed. The objects stop being places and start being populations. The catalogue stops listing individuals and starts estimating totals. And the distance between what is there and what has been seen begins to open up in a way that does not close again for the rest of the night. Past Mars, the census changes character for the first time. The objects stop having individual histories and start having statistics. Between the orbits of Mars and Jupiter lies the main belt of asteroids, and it contains something on the order of 1.4 million catalogued objects larger than a kilometer across. Hundreds of millions of smaller ones are inferred from the size distribution, but have never been individually detected. It is by a very wide margin the most populous catalogued region in the sphere, and it weighs almost nothing. The entire main belt, all 1.4 million catalogued bodies and everything beneath them, comes to roughly 4% of the mass of the Moon. About a third of that total sits in a single object, a round dwarf world some 940 kilometers across, which holds more mass than the next several largest bodies combined. Take that one object away, and the remainder of the belt is a fine scattering of gravel spread across a region hundreds of millions of kilometers wide. This low mass was, for a long time, a genuine problem. The obvious explanation for a belt of rubble is a planet that failed to form, and if that were the story, the belt should contain something close to a planet's worth of material. It does not. It contains 1,000th of that. The current understanding is that the region was not a failed planet but a cleared one. As Jupiter grew and shifted in its orbit, its gravity swept the belt repeatedly, flinging the great majority of the original material inward toward the Sun or outward past Neptune. What remains is the small fraction that happened to be in the right place to survive the clearing. The belt is also, and this is the part that contradicts every dramatic depiction, profoundly empty. The average separation between belt objects larger than a kilometer is on the order of 1,000,000 kilometers. That is several times the distance from the Earth to the Moon. If you were standing on one asteroid, you would almost certainly not be able to see another one, and if you could, it would be a faint point of light, indistinguishable from a star. Every machine ever sent through the belt has crossed it without incident, and in the planning of those missions, the crossing was never the difficult part. It was not even a serious concern. There is a further piece of structure worth noting. The belt is not uniform. It is cut through by gaps, narrow ranges of distance from the Sun where almost nothing orbits. These gaps exist because an object at that distance would complete a simple whole number ratio of orbits for every one of Jupiter's, and would therefore receive a small gravitational nudge in the same direction at the same point over and over again. Over millions of years, the nudges accumulate and the orbit becomes unstable. The object is removed. The gaps are not leftovers from some earlier arrangement. They are maintained continuously, cleared and re-cleared for as long as Jupiter has been where it is. Sharing Jupiter's own orbit are two further swarms, sitting ahead of the planet and behind it at the 2 points where the gravity of the Sun and the gravity of Jupiter combine to hold objects in a stable pocket. These swarms are thought to rival the main belt in number. They are dark, they are red, and their composition suggests that most of them did not form where they now sit. They appear to have been captured from the outer system during the early rearrangement of the giant planets, scooped up and locked into place, and they have stayed there ever since. Between the giant planets drift the centaurs, and they are the most transient population in the inner sphere. These are icy bodies on unstable orbits that cross the paths of the giants. Each close pass changes the orbit. Some are flung inward, where they warm and begin to shed gas and become comets. Others are flung outward and lost. The typical lifetime of a centaur, from arrival to removal, is measured in a few million years. That is far shorter than the age of the solar system, which means the population cannot be original. It must be continuously resupplied from somewhere further out, and that requirement is one of the reasons we know the outer reservoirs exist at all. Now the second list again, which records how much of these millions of objects we have actually seen. Here the record is mixed, and it depends entirely on where the object is and where it is going. For the near-Earth objects, the small population whose orbits bring them close to our own, the ledger is genuinely good because a great deal of deliberate effort has gone into it. Essentially, every near-Earth object larger than a kilometer across is believed to be catalogued, and its orbit is known well enough to project forward for centuries. That is a completed piece of work, and it took decades of dedicated sky surveying to finish. Below a kilometer, the completeness falls away steeply. For objects around 140 meters, perhaps 40% are known. For objects a few tens of meters across, large enough to do serious damage to a city, the catalogue is a small fraction of the true population. Such objects are routinely discovered days before their closest approach, and occasionally after it. They are found then not by looking for them, but by noticing them as they leave. For the main belt itself, the catalogue is large, but the knowledge is thin. A few dozen asteroids have been visited or photographed at close range. Everything else is a moving dot in a survey image, tracked across nights and fitted to an orbit. The composition, the shape, the rotation, the surface, all of it is inferred from how the brightness changes as the object turns. And where machines have actually arrived, the surfaces have consistently been stranger than expected. Several asteroids turned out to be loose piles of rubble held together by gravity and the faintest cohesion, rather than by rock. A machine that touched one found the surface so soft and so mobile that material flowed like a fluid. Others are contact binaries, two separate bodies resting against one another, joined but never merged. Some have moons of their own, small companions circling objects only a few kilometers across. There is a subtlety in all of this that governs the entire rest of the census, and it is worth stating plainly here where it is still small. Whether an object is found depends at least as much on how reflective it is as on how large it is. A bright, pale body 100 meters across can be easier to detect than a dark one twice that size. The outer populations of the solar system are almost uniformly dark. Their surfaces have been irradiated for billions of years and reflect only a few % of the light that falls on them. So the catalogs do not simply thin out with distance. They thin out with distance and with darkness at the same time, and the two effects multiply. The smallest members of these populations announce themselves in a different way. Objects a meter or so across enter the Earth's atmosphere several times a year. Almost none of them are ever seen beforehand. They are detected by the flash as they arrive, recorded by cameras and by instruments listening for the low sound that follows, and reconstructed afterward from where the fragments fell. For that entire size range, the observation and the arrival are the same event. Even the largest object in the belt holds unfinished business. The round dwarf world at the center of the belt's mass budget appears to carry a substantial fraction of water ice, and bright deposits of salt sit on its surface where something briny seems to have reached the top and evaporated. Whether there is still liquid down there, held in pockets rather than in an ocean, is not settled. A machine spent years in orbit around it, photographed it thoroughly, and the question remains open. There is one detail in the catalogue that quietly says a great deal about the observational situation. A number of catalogued near-Earth objects are almost certainly not natural. They are pieces of spent hardware from early spaceflight, left on solar orbits, occasionally rediscovered decades later and briefly logged as new asteroids before their orbits give them away. The sky is large enough and the objects faint enough that we lose track of things we ourselves put there. That is the useful idea to carry forward from this shell. There is a difference between an object being present and an object being known, and this is the region where that difference is smallest and most manageable. Everything from here outward widens the gap. Beyond Neptune, at about 30 astronomical units from the Sun, the character of the census changes again, and this time the change is permanent. The objects become icy rather than rocky. The orbits become long enough that no human observation program will ever watch one complete. And the catalogue, which up to this point has been merely incomplete, begins to collapse. The main body of this population occupies a band between roughly 42 and 48 astronomical units from the Sun. Something on the order of 5,000 objects have been catalogued there and in the surrounding structures. Models of how the region formed and of how many objects must exist to produce the ones we do see suggest that more than 100,000 bodies larger than 100 kilometers across are out there, with a great many more below that size. The catalogued fraction is small, and it is heavily biased toward whatever happens to be largest, brightest, and closest. The population is not one thing. It divides into at least 3 families, and the divisions tell a story about the early history of the system. The classical objects sit on nearly circular orbits, tilted only slightly from the plane of the planets, apparently undisturbed since they formed. They are the quietest population in the outer system. Nothing has happened to them. Whatever arrangement they settled into during the first few tens of millions of years, they have kept. The resonant objects are locked into simple ratios with Neptune. The largest group completes exactly 2 orbits for every 3 that Neptune completes. This sounds like a fragile arrangement, and it is the opposite. The resonance is what protects them. Because the timing repeats exactly, the 2 objects never meet at close range. They are choreographed, and the choreography has held for billions of years. The largest member of this group is the best-known world beyond Neptune, and its safety from that planet is entirely a matter of timing rather than distance. Their orbits cross. They simply never arrive at the crossing at the same moment. The scattered objects are the survivors of something rougher. Their orbits are highly stretched and often steeply tilted. At their closest approach, they come near enough to Neptune to be gravitationally kicked, and at their farthest, they reach out to hundreds of astronomical units. They are, in effect, still being processed. Each pass changes the orbit slightly. Over long enough timescales, some of them will be thrown much further out, and some will be lost from the system entirely. And then, at about 48 astronomical units, the population stops. This is one of the genuinely unresolved features of the outer solar system, and it deserves to be stated plainly because it is easy to skip past. Across a fairly narrow range of distance, the number of objects drops by a large factor and does not recover. There is no gradual thinning. There is a band of material, and then a step down, and then very little. Something set an outer boundary on the region where this population formed, or something removed the material beyond it afterward. The candidate explanations are all reasonable, and none is established. The original disk of material out of which everything formed may simply have ended there. A star passing close by while the Sun was still inside its birth cluster may have truncated the disk, stripping away everything beyond a certain distance in a single encounter. Or the region may have been sculpted over billions of years by the gravity of a massive body further out that has not yet been found. These remain open questions with observational work still running, and it is worth holding them as questions rather than as answers. The mass of the region is the other surprise. The entire population beyond Neptune is estimated at around 2/100ths of an Earth mass. Perhaps as little as 1/100th. That is a tiny amount of material spread across an enormous volume, and it is nowhere near enough. The problem is that you cannot build the objects we can see out of that little material. To assemble bodies of 1,000 kilometers and more, through slow collisions at low speeds, the region must originally have held something on the order of 10 to 30 Earth masses, which means that more than 99% of the original material is gone. It was thrown outward into the far reaches by the migrating giant planets, or thrown inward and consumed, or ejected from the solar system altogether. What remains beyond Neptune is not a population. It is a residue. Now the parallel question, and here the answer becomes very short. Exactly one object in this entire region has ever been examined at close range. It is a small, dark, reddish body at about 44 astronomical units, and it turned out to be two rounded lobes resting against one another, joined at a narrow neck. The shape is remarkable because it preserves the moment of its own formation. The two lobes did not collide. They approached each other at something like walking pace and settled together, and they have been resting like that, undisturbed, ever since. It is one of the most pristine things ever photographed, a piece of the original construction of the solar system that nothing has happened to in 4.5 billion years. The same machine, some years earlier and much closer in, had passed the largest of the resonant worlds at about 33 astronomical units, and what it found there rearranged a great deal of thinking about how cold a world can be and still be active. There were mountains of water ice several kilometers high, standing up, because at those temperatures water behaves as bedrock. There was a broad, smooth plain of frozen nitrogen, with no impact craters on it at all, which means the surface is being renewed, slowly, from below. The plain is divided into polygonal cells, tens of kilometers across, the signature of material convecting upward in the middle of each cell and sinking at the edges, on a timescale of centuries. and there were layers of blue haze in the thin atmosphere, stacked one above another to a height of 200 kilometers. None of that had been predicted. A world receiving a fraction of a thousandth of the sunlight that falls on Earth was expected to be inert, and it is not. That object is the most distant thing inside tonight's sphere that has ever been seen at close range. 44 astronomical units, against a boundary at 63,241. It sits at about 1/1400th of the sphere's radius, and everything beyond it, in every direction, has never been visited by anything. The rest of the region is points of light, or less. The largest bodies have been resolved into a handful of pixels by the most powerful telescopes available, enough to measure a rough size and a color, and occasionally to spot a moon. Below that, objects are single, unresolved dots that shift very slightly against the background stars from one night to the next, and the shift is the entire detection. For anything smaller than roughly 100 kilometers, even that is not possible. Those objects are found by a technique that is more like listening than looking. A telescope watches a background star. If an unseen body happens to pass precisely between that star and the telescope, the star flickers for a fraction of a second. Nothing is learned about the object except that it exists and roughly how large it must be. That flicker is the whole observation. Surveys built on this method have recovered a small number of detections, and the population estimates that follow from them disagree with each other by a factor of 10. Some details of what is out there are nonetheless known, and they are quietly lovely. The largest bodies are round, layered, and carry thin atmospheres that freeze onto the surface as the object moves away from the sun and lift again when it returns. At least one has a moon roughly half its own diameter, which makes the pair closer to a double world than to a planet and a satellite. The two of them turn about a point that lies in the empty space between them. The colors run from neutral gray to a deep dark red, and the redness is thought to come from billions of years of radiation slowly working on simple ices, taking them apart and reassembling them into complex organic residues. Nothing resurfaces these bodies. There is no weather, no impact gardening to speak of, and no warmth. Whatever color a surface acquires, it keeps. Some of the orbits are startling. A number of objects travel on paths so steeply tilted that they move nearly perpendicular to the plane of the planets, rising far above the system and falling far below it. At least one travels backwards around the sun, against the direction of everything else. No process operating in a flat disk produces those orbits. They are evidence of something that happened afterward. And for many of these bodies, the most basic facts remain unmeasured. The rotation periods of a great number of them are simply unknown, because at that distance, the brightness variations are too small and too slow to separate from noise. Predicted surface temperatures run around 40 to 50 Kelvin. That is cold enough for nitrogen and carbon monoxide to sit on the ground as solids. There is a second structure inside the sphere, and it is not made of objects at all. It is made of moving gas and magnetic field, and it has a definite edge that has been physically crossed and measured. The sun does not simply shine. It also leaks. Its outer atmosphere is so hot that its own gravity cannot hold it, and it streams away continuously in every direction as a wind of charged particles. About 1 million tons of the sun departs this way every second, traveling outward at somewhere between 400 and 800 kilometers per second. That wind fills the space between the planets. It is what makes comet tails point away from the sun rather than trailing behind the comet. It is what produces auroras when it meets a planet with a magnetic field. And it is thin beyond any ordinary sense of the word, a few particles per cubic centimeter near the Earth, falling steadily with distance. The wind does not fade out gradually. It travels at full speed until the pressure of the gas between the stars becomes comparable to its own, and at that point, it slows abruptly. That deceleration is a standing shock, sitting at roughly 85 to 95 astronomical units from the Sun. Past the shock, the slowed and heated wind piles up in a turbulent region and finally stops entirely at a boundary called the heliopause, at about 120 astronomical units. That boundary is the outer surface of the bubble the Sun blows in the surrounding gas. Inside it, the environment is the Sun's own exhalation. Outside it, the environment is the galaxy. What makes this part of the census unusual is that the boundary was not deduced or modeled or imaged from a distance. It was crossed. Two machines built in the middle of the last century, launched to study the outer planets and never designed for this, kept going afterward, and each of them eventually passed through. They both recorded the same signature, years apart and in different directions. The density of charged particles around them rose by a factor of roughly 40, from about 0.002 of a particle per cubic centimeter to about 0.08. Nothing dramatic happened. There was no wall and no crossing sensation. There was simply a change in a number, transmitted home over many hours, and that number was the edge of everything the Sun can physically reach. Even that description overstates the certainty, because the shape of the structure is not settled. It is certainly not a sphere. The Sun is moving through the local interstellar gas at some tens of kilometers per second, which compresses the bubble on the leading side and stretches it behind. Competing models describe the result as comet-shaped, with a long trailing tail, or as something closer to a croissant, with two rounded lobes and no real tail at all. Nothing has ever observed the structure from outside, and nothing will for a very long time. We are inside it, which is the worst possible place from which to determine its shape. One attempt to map it produced a genuine surprise. By detecting neutral atoms that are created at the boundary and travel back inward in straight lines, unaffected by magnetic fields, it was possible to build a rough picture of the whole surface. The picture showed a bright ribbon arcing across it, a band of enhanced emission that no model had predicted and that is still only partly accounted for. It is probably an alignment effect, related to the direction of the interstellar magnetic field where it presses against the bubble. Probably. The map of our own boundary has a feature on it that we cannot fully explain. There is something worth pausing on in the way the crossing was detected, because it says a great deal about how thin all of this is. The instrument that made the measurement was not designed to work at the boundary. Its intended sensor had failed long before. What it could still do was listen. When a burst of activity from the Sun eventually reached the machine, years after leaving, it set the surrounding gas ringing at a frequency that depends directly on how many particles are present. The machine heard a faint tone, and the pitch of that tone gave the density. That is how the edge of the Sun's domain was measured. Not by a photograph, not by a detector reading, but by the note the local gas sings when something disturbs it. The bubble is also not a permanent structure. Its size is set by the balance between the wind pushing outward and the interstellar gas pressing inward, and the gas the Sun is moving through changes. Every few 100,000 to few million years, the Sun enters a region of different density, and the bubble expands or contracts accordingly. There have very likely been periods when the boundary sat far closer in than it does now, and periods when it stood much further out. Nothing catastrophic follows from either. The inner planets carry their own magnetic shields and their own atmospheres, and the change is measured in the amount of cosmic radiation arriving, rather than in anything visible from the ground. And the total amount of material involved is smaller than the scale of the structure suggests. The wind is so thin that all the solar wind in flight inside the entire bubble, out to 120 astronomical units in every direction, amounts to a few tens of millions of tons. That is a structure 120 times wider than the Earth's orbit, made of less material than a small mountain. Two things about this structure matter for the census, and they point in opposite directions. The first is scale. This entire domain, the whole region the sun's wind can physically reach, has a radius of about 1/500th of tonight's sphere. In volume, that is roughly 100 millionth. Everything the sun blows, everything it can touch with its own material, occupies 100 millionth of the space we are counting. If the heliosphere were the solar system would be a very small dot indeed. The second is that the heliopause is not a gravitational boundary at all, and it is easy to conflate the two. The sun's wind stops at 120 astronomical units. The sun's gravity does not. Gravity weakens smoothly with distance and never reaches zero, and there are trillions of objects held on bound orbits far beyond the heliopause, in a region the solar wind has never entered and never will. The sun's influence ends there. The sun's possessions do not. That distinction is the pivot of tonight's count. Up to this point, we have been listing things that have been detected. From here outward, we will be listing things that have been inferred. Before we cross that line, it is worth taking stock of what is actually out there in machine terms, because it is a small and rather moving inventory. 5 objects built on Earth are currently on trajectories that will carry them out of the solar system. 2 are the pair that crossed the boundary. 2 others, launched slightly earlier, went silent decades ago and are still traveling. The 5th was sent to the outer belt and is now heading outward with its work behind it. Their speeds run between about 11 and 17 kilometers per second. The farthest of them is around 170 astronomical units out. Its radio signal, transmitted at a power comparable to a domestic light bulb, takes roughly a full day to reach us, arriving with a received strength measured in a small fraction of a billionth of a watt. It is recovered only because the exact frequency is known in advance, and the receiving equipment can listen for that one narrow line and ignore everything else. At 17 kilometers per second, that machine will need something over 17,000 years to reach the edge of tonight's sphere. It has been traveling for less than half a century. It has covered about 1/370th of the distance. There are some quieter facts about the boundary that are worth carrying forward. The bubble partially shields everything inside it from the cosmic rays of the galaxy, and the shielding varies with the sun's activity cycle. When the sun is quiet, more of that radiation reaches the inner system. Interstellar atoms that carry no electric charge drift straight through the heliopause as though it were not there, and they have been detected close to the Earth. So have grains of interstellar dust, which means that material from beyond the boundary has already been physically captured and analyzed in laboratories, without anything traveling out to fetch it. It came here. And the boundary is not at one distance. Because of the compression at the nose and the stretching at the tail, the answer to how far away the edge of the heliosphere is depends entirely on which direction you leave in, by a factor of several. Even the one edge of the solar system that we have measured directly turns out to be a different distance, depending on where you stand. This is a reasonable place to stop and gather what we have counted so far, because from here the numbers stop being familiar and the sphere begins to open up in earnest. We began with a boundary at 63,241 astronomical units, and we noted that nothing in nature marks it. Inside that boundary we found one star holding 99.86% of the mass, 8 planets amounting to 446 Earth masses, and 300 moons amounting to an eighth of one. We found a belt of rubble weighing 4% of the Moon, spread so thinly that crossing it is not a hazard. We found a residue beyond Neptune, 100,000 icy bodies that are all that remains of 30 Earth masses of original material. And we found a bubble of solar wind reaching 120 astronomical units, whose edge has been crossed and measured by 2 machines. All of that together occupies a region 120 astronomical units in radius. We have 500 times further to go, and the volume grows as the cube. Just past the edge of the wind, in a region where nothing has been visited and very little has been detected, sits a small group of objects with orbits that should not exist. The best known of them is a reddish world roughly 1,000 kilometers across. Its closest approach to the Sun is about 76 astronomical units, which means it never comes anywhere near the planets. Its farthest point is around 937 astronomical units. One orbit takes about 11,400 years. When it last passed this way, there was no writing anywhere on Earth, and the last ice age had only recently released its grip. A second object has a closest approach near 80 astronomical units. A third reaches out to some 2,000. There are only a handful of them known, and collectively they are called the detached population, because they are detached from the influence of the planets entirely. These orbits are a problem, and it is worth being precise about why. An object on a stretched orbit has usually been put there by a close encounter with something massive. That is how the scattered objects beyond Neptune acquired their paths. But these bodies never come close enough to Neptune, or to anything else in the current solar system, for that explanation to work. Nothing that is here now can have placed them where they are. And the Sun's present galactic surroundings are far too gentle to have lifted their orbits from within, because at 76 astronomical units, the Sun's grip is still firm, and the outside universe has almost no leverage. So something else did it, and there are 3 candidate explanations, all interesting, none established. The first is that a star passed close by during the Sun's first few million years. The Sun did not form alone. It formed inside a cluster of hundreds or thousands of stars, packed far more tightly than anything in our neighborhood today, and in such an environment close approaches would have been ordinary rather than rare. A star passing at a few hundred astronomical units would lift the orbits of everything in the outer disk, leaving exactly this kind of detached population behind. The second is stranger and follows directly from the first. During such an encounter, material does not only get lifted, it also gets exchanged. Some of these objects may not have formed here at all. They may have been captured from the disk of another star during a passage that lasted a few thousand years, and they have been orbiting the Sun ever since as permanent guests. There is no way at present to tell which, if any, they are. The third is that a body of several Earth masses on a distant and eccentric orbit has been shepherding this population for billions of years, gradually organizing their orbits into the pattern we observe. This remains a live hypothesis with observational tests still running. It should be held exactly as that, an open question that current surveys are working through, with the possibility that the apparent pattern is an artifact of where and how we have been looking. But the explanations are less important than a simpler observation about the objects themselves, and it is the observation that governs the entire rest of the count. Every single one of these bodies was discovered while near the closest point of its orbit. That is not a coincidence. It is a consequence of how light behaves across distance, and the arithmetic is unforgiving. Sunlight has to travel out to the object, reflect, and travel back. Both journeys dim it by the square of the distance, so the total dimming goes as the fourth power. Double an object's distance and it becomes 16 times fainter. Multiply the distance by 10 and it becomes 10,000 times fainter. Apply that to the reddish world. At its current position, near 76 astronomical units, it is detectable by a large telescope. At its farthest point, 937 astronomical units, it would be roughly 20,000 times fainter, well beyond anything that can be seen. Which means that of its 11,400-year orbit, it spends something like 1% of the time in a position where it can be found at all. For the other 99%, it is simply absent from every catalogue. We found it because we happened to be looking during its brief visible window, in the small handful of decades in which the necessary instruments existed. Turn that around, and the implication is unavoidable. For every detached object we have found, the statistics require a large population currently sitting out at hundreds or thousands of astronomical units, entirely undetectable, waiting for their own brief windows. We are not looking at a small population. We are looking at the visible 1% of a population whose size we can only estimate. The conditions out there are worth a moment on their own. At 900 astronomical units, the Sun delivers roughly a millionth of the light it delivers here, which is still brighter than full moonlight on Earth, and which is not nothing. It would be enough to read by, but it carries almost no heat. Surface temperatures at those distances fall to around 12 Kelvin, cold enough that even neon would be approaching its freezing point. There is no weather, no resurfacing, no erosion. Whatever is on the surface stays where it is. And so the redness makes sense. These objects have sat in cosmic radiation for 4.5 billion years, and that radiation has slowly broken apart the simple ices on their surfaces and reassembled the fragments into heavier organic compounds. The result is a dark, deep red crust, laid down over billions of years, with nothing to disturb it. They are the most patiently colored objects in the sphere. It is worth describing how such an object is found, because the method explains its own limits. A telescope photographs the same patch of sky several times over a night. The images are then subtracted from one another. Everything that has stayed still cancels out, and what remains is anything that moved. Stars stay still. Distant solar system objects crawl. So the detection is not really of an object at all. It is of a displacement, a few pixels of motion between one exposure and the next. That method has a flaw built into it. The further out a body is, the more slowly it appears to move, and beyond a certain distance, the motion over a single night becomes smaller than the measurement error. At that point, the object stops distinguishing itself from a very faint star, and the entire technique stops working, regardless of how sensitive the telescope is. Which brings us to the emptiest part of tonight's census, and it is not the far reaches. It is the middle. Between roughly 100 astronomical units and roughly 2,000, there is a band of the sphere in which we have detected almost nothing at all. It is too far out for reflected sunlight to survive the fourth power dimming. It is too close in for the statistical arguments that describe the far reaches to say anything useful about individual objects. And nothing has ever traveled through it. The farthest machine will not reach the near edge of that band for another 9,000 years. So there is a shell of space around this solar system, beginning just past the last detected objects, and extending outward for 2,000 times the Earth's distance from the Sun, about which we can say almost nothing with confidence. Not that it is empty, only that it is unexamined. One more consequence of the distances. No human observation program will ever watch one of these bodies complete a full orbit. Every path we have for them is reconstructed from a short observed arc, a few years of measurement fitted to a curve that will take 11,000 years to close. We know where they are going, but the knowledge is entirely mathematical. Nobody will ever check it. We come now to the part of the census that answers the question in the title, and the answer is a single population that nobody has ever seen. Almost everything inside 1 light-year of Earth belongs to an enormous, roughly spherical shell of icy bodies surrounding the Sun at enormous distance. It is not a belt. It is not a disk. It is a shell, enclosing the entire solar system in every direction, above the plane of the planets as thickly as within it. And it is the true bulk of the Sun's territory. The structure is thought to have 2 parts. There is an inner region, flattened into a thick torus, extending from perhaps 2,000 out to 20,000 astronomical units. And beyond it an outer region, genuinely spherical, extending from 20,000 to perhaps 100,000 astronomical units, and possibly further. 1 light-year, at 63,241 astronomical units, falls inside that outer region. Roughly 2/3 of the way through it. Tonight's boundary does not enclose this cloud. It cuts through it. The numbers involved are difficult to hold. Something on the order of 1 trillion objects larger than a kilometer are thought to exist in the outer region alone. The inner region, being denser, may hold 5 to 10 times as many again. That is a population several times larger than the number of stars in this galaxy, all of it bound to one ordinary star, all of it invisible. And the whole thing weighs almost nothing. The total mass of the cloud is a matter of genuine disagreement, with credible estimates ranging from under 1 Earth mass to a few Earth masses. Even at the upper end, 1 trillion objects amount to less than the mass of the planet you are lying on. They are simply spread across a volume so enormous that a planet's worth of material fills it. The conditions out there deserve to be described slowly, because they are close to the quietest conditions physically available in this galaxy. Start with temperature. At 50,000 astronomical units, sunlight is so weak that it is no longer the dominant source of heat. If you calculated the temperature of an object out there from sunlight alone, you would get about 1.2 Kelvin, which is to say, very nearly nothing. But the objects are not that cold, because there is a floor underneath them. The universe itself has a temperature. The radiation left over from the earliest era of cosmic history fills all of space at 2.73 Kelvin, and nothing anywhere can be colder than its surroundings without a mechanism to make it so. So the bodies in the outer cloud sit at about 3 to 4 Kelvin. The Sun contributes a fraction of a degree. Everything else is the residual warmth of the universe. These objects are, quite literally, at the temperature of the cosmos, and they have been for 4.5 billion years. Then consider how slowly they move. Orbital speed falls with distance from the Sun. The Earth travels at about 30 kilometers per second. Neptune manages about 5.5. At 50,000 astronomical units, an object on a circular orbit moves at roughly 130 meters per second. That is worth converting. 130 meters per second is slower than a passenger aircraft at cruise. Out at the very edge of the cloud, orbital speeds fall below the speed of a car on a motorway. These are not objects hurtling through space. They are drifting at something close to the pace of ordinary human travel, and they have been drifting for the entire age of the solar system, which follows into the periods. An orbit at 50,000 astronomical units takes about 11 million years to complete. At 1 light-year, it takes roughly 16 million. Since the Sun formed, an object out at tonight's boundary has completed fewer than 300 orbits. 300 years at the sphere's edge is a single day, The entire history of complex life on Earth is a handful of turns. And then the spacing, which may be the most striking number in the whole census. There are 1 trillion objects out there, which sounds crowded. But the volume is so large that the typical distance from one comet to its nearest neighbor is somewhere between 15 and 35 astronomical units. That is the distance from the Sun to Uranus. Between neighbors. If you were standing on one of these bodies, you would see nothing of the others at all. Not a glow, not a scattering of nearby points, nothing. The nearest one would be as far from you as Saturn is from the Sun, and it would be a dark object a few kilometers across at that distance. You would see a sky full of stars, and one of those stars would be slightly brighter than the rest. That would be the Sun, at about magnitude -3, roughly as bright as Jupiter appears from Earth, giving no warmth whatsoever. Now the parallel question, and for this section the answer is the shortest in the entire episode. Nothing about this population has ever been observed. Not one object. No telescope has ever imaged a body in the outer cloud. No machine has ever approached one. Every number given above is an inference. The chain of inference is worth explaining because it is genuinely elegant, and it is the reason we can speak about the cloud with any confidence at all. Long-period comets fall into the inner solar system on extremely stretched orbits. When one appears, its path can be measured over several months and traced backward. Do that for many comets, and 2 things emerge. The first is that their farthest points cluster at tens of thousands of astronomical units, over and over again, from comet after comet. The second is more revealing. Their orbital inclinations are isotropic. They arrive from every direction equally, from above the plane of the planets as often as from within it, and traveling backwards as often as forwards. A flattened disk cannot produce that. Only a spherical shell can. The entire structure was deduced from the arrival statistics of the objects that leave it. We have never seen the cloud, but we have seen a great many things that came from it, and they all arrive in a pattern that only one shape explains. What dislodges them is as quiet as everything else out there. At those distances, the Sun's grip is so weak that the smoothed gravitational pull of the galaxy itself, the combined tug of hundreds of billions of distant stars, can slowly torque an orbit. Over millions of years, it lowers the closest approach, a little at a time, until at last the object's path dips into the inner solar system and it becomes a visible comet. Passing stars do the same job more abruptly. There is something worth sitting with in that. When a comet appears in an Earth sky, the process that sent it here began millions of years earlier. Its departure from the cloud is older than the human species. It has been falling, quietly and without acceleration worth speaking of, for longer than there have been people to see it arrive. A few further things are known, or reasonably suspected. Most of these bodies are probably not natives of the outer system at all. They are thought to have formed near the giant planets and to have been flung outward during the first few tens of millions of years, which makes the cloud a population of exiles rather than a population of originals. A meaningful fraction may have been captured from other stars during the Sun's time in its birth cluster, and a comparable amount of the Sun's own material is now presumably orbiting other stars. Comets on their first approach show unusually strong activity while still far from the Sun, which is consistent with surfaces holding extremely volatile ices that have never been warmed by anything. There is one honest qualification to make to the claim that nothing from the cloud has ever been seen, and it improves the picture rather than undermining it. Machines have flown past several comet nuclei at close range, and one machine orbited a comet for 2 years and placed a small lander on its surface. So we have detailed photographs of bodies of the same general kind, dark, dusty, porous, held together weakly, with surfaces blacker than charcoal, and interiors that appear to be more empty space than solid material. Those particular comets came from the nearer reservoir beyond Neptune rather than from the outer shell, but the family resemblance is expected to be close. We have never seen the cloud. We have seen, in considerable detail, a handful of objects that almost certainly resemble its members. There is also a structural relationship between the two parts of the cloud that matters. The outer region is loosely held, and a close stellar passage can strip a significant fraction of it away. If that were the whole story, the outer cloud would have been emptied long ago. It survives because the inner region is bound far more tightly and is much harder to disturb, and it slowly leaks objects outward to refill what is lost. The inner cloud is the reservoir behind the reservoir. And the whole structure has an outer limit, set not by any material boundary, but by the point at which the sun's gravity finally loses to the galaxy. That limit lies somewhere between 100,000 and 200,000 astronomical units, which is to say between 1.5 and 3 light-years. Tonight's sphere reaches well short of it. The sun's actual territory extends past our boundary in every direction. Direct detection has been attempted and has failed. The objects are too cold to shine and too small to occult often. The most promising method for the future is statistical, watching enough background stars for long enough to catch the fractional second flicker of a kilometer-scale body at tens of thousands of astronomical units. That work is slow, and so far it has produced no confirmed detection. The census has been running alongside a second list all night, and it is time to read that second list out in full. It records, of everything inside 1 light-year of Earth, how much has ever actually been seen. The answer comes in tiers, and it is best delivered as an inventory, calmly, without apology. The first tier is what human beings have visited in person. The farthest any person has ever traveled from the Earth is a little over 400,000 kilometers on a loop that carried a crew around the far side of the Moon. In astronomical units, that is about 2/1000ths of one. Expressed as a fraction of tonight's radius, it is roughly 400ths of a millionth of 1%. Every human being who has ever lived, every civilization, every language, every idea anyone has ever had, has occurred inside a region that on this scale is indistinguishable from a single point. The second tier is what machines have seen at close range. Here, the record is much better and genuinely impressive. Machines have flown past or orbited every planet. They have photographed dozens of moons, several asteroids, a handful of comet nuclei, and exactly one object in the belt beyond Neptune, at about 44 astronomical units. That last one is the record, and it is unlikely to be broken soon. 44 astronomical units, as a fraction of 63,241, gives a volume ratio of about 1/3 billionth. Everything humanity has ever photographed from close range within this sphere fits inside 3 billionths of it. The third tier is what has been measured in place. 5 machines carry instruments outward past the planets, and the farthest is around 170 astronomical units. Every direct physical measurement ever made of the material environment of space, every particle count, every magnetic field reading, every measurement of density or temperature or composition was made inside a bubble of that radius. As a fraction of tonight's volume, that bubble is about 1/50 millionth. The fourth tier is what has been detected at all, by any means, at any distance. The most distant objects ever detected in this sphere sit at 100 or so astronomical units. Being generous and taking 100 astronomical units as the outer edge of the detected region, the fraction of the sphere's volume in which we have ever detected anything comes to about 4 parts in a billion. 4 parts in a billion. That is the honest answer to the question. Of the space within 1 light year of where you are, we have detected something in about 4 billionths of it, and the remaining volume is known entirely by inference from the small number of objects that have fallen inward and made themselves visible. The 5th tier is everything else. More than 99.9999% of the volume and the great majority of the objects have never been observed by anything, and on current understanding, never will be individually. It is important to say why, because the reason is not a lack of effort or of instruments. The reason is a piece of physics that cannot be worked around. Reflected sunlight dims twice. It weakens as the square of the distance traveling out from the sun to the object, and it weakens again as the square of the distance traveling back from the object to the telescope. The total dimming, therefore, goes as the 4th power of the distance. That single fact governs the entire outer sphere. Work the ladder. A large, reasonably reflective body at 100 astronomical units is at the practical edge of what current surveys can find. The same body at 1,000 astronomical units is 10,000 times fainter. At 10,000 astronomical units, it is 100 million times fainter. And at the edge of tonight's sphere, it is roughly 200 billion times fainter than it was at the start of the ladder. There is no instrument that closes a gap of 200 billion. There is no instrument being designed that closes it. The largest survey telescopes now operating can detect objects some 50 million times fainter than the dimmest star a dark-adapted human eye can see, and that capability, extraordinary as it is, falls short by a factor of thousands. Detecting the heat instead does not rescue the situation. A body at 3 or 4 Kelvin radiates almost entirely at sub-millimeter wavelengths, at an intensity so low that it is indistinguishable from the cold dust of the galaxy lying in front of it and behind it. The signal is not merely faint. It is buried under a foreground that cannot be subtracted. And there is a third obstacle, which is more subtle and in some ways more final. Surveys find distant objects by their motion between exposures. An object at tens of thousands of astronomical units barely moves at all against the background stars, not over a night, not over a year, not over a human lifetime. Its parallax shift would be tiny and its proper motion negligible. Even if it were somehow bright enough to see, it would be indistinguishable from a very faint, very distant star. The handle we use to separate solar system objects from the background is gone. This leaves exactly one workable technique for the outer sphere, and it is the technique of watching for shadows. If a body passes precisely between a background star and a telescope, the star flickers for a fraction of a second. That flicker is the entire observation. It reveals that something exists and roughly how large it is, and nothing else. No color, no composition, no orbit, no distance beyond a rough estimate. Surveys built on this method have produced a handful of ambiguous events, and the population estimates derived from them disagree with each other by an order of magnitude. That is the complete toolkit for 99.99% of the volume of tonight's sphere. Watching for shadows that last a fraction of a second, and counting how often they happen. Every catalogue of the outer solar system is therefore biased in 3 directions simultaneously. Toward large objects, because small ones are too faint. Toward bright surfaces, because dark ones reflect almost nothing and the outer populations are almost uniformly dark. And toward objects currently near the closest points of their orbits, because that is the only time they are within reach. Any statement about what is out there has to be corrected for all three biases at once, and the corrections are large. It is worth making the consequence concrete, because in the abstract it stays comfortable. Suppose there were a world out there. Not a comet, not a fragment, but a genuine planet, several times the mass of the Earth, sitting quietly at 5,000 astronomical units. Cold, dark, unlit by anything, on an orbit taking hundreds of thousands of years. We would not know. There is no survey running that would find it. It would be far too faint in reflected sunlight, far too cold to shine in the infrared against the galactic foreground, and far too slow-moving to separate from the background stars. It could have been there for the entire history of the solar system, and the first indication of its existence would be a subtle statistical pattern in the orbits of objects it had disturbed. That is precisely why the question of a distant massive body remains open. Not because the evidence is strong, but because the absence of a sighting means almost nothing at those distances. Turn the same idea outward, and it becomes clearer still. If an exact copy of our solar system existed at the edge of tonight's sphere, 1 light-year away, we would see its star without difficulty. It would be an unremarkable point of light among the others. We would see none of its planets. None of its moons, none of its belts, none of its comets, none of its outer shell. Everything we have spent this episode counting would be entirely invisible from a distance we consider close. And that is a useful way to hold the whole ledger. Our instruments are not weak. They are extraordinary. They can measure the composition of an atmosphere on a planet orbiting another star, and detect the wobble of a star being pulled by a world too faint to image, and record a signal from a machine 170 astronomical units away that arrives with less energy than a snowflake landing. None of that is enough. The sphere is simply large in a way that instruments do not scale against, because sensitivity improves by factors of 10, while distance punishes by factors of 10,000. The honest picture is this. We are standing in a dark field at night. We can see the ground within arm's reach in fine detail, every blade of grass. Slightly further out, we can make out shapes. Beyond that, there is nothing but the sense that the field continues and the occasional certainty that something has moved out there, because now and then something wanders close enough to be seen before returning to the dark. That is not a failure of eyesight. It is a statement about the size of the field. There is one small and rather touching exception to all of this, and it is worth ending the ledger on. The only material from beyond the boundary of the sun's wind that human beings have ever physically held consists of individual grains of interstellar dust captured by instruments near the Earth. Not fetched. Not retrieved by any journey. They drifted in through the heliopause on their own because they were small and uncharged enough to pass through, and they were caught here and measured. We have never gone out to the sphere. But a very small amount of the sphere has come to us. Not everything inside the sphere belongs to it. A significant portion of the contents is simply passing through and has no relationship with the sun at all. Interstellar objects are bodies that were ejected long ago from other star systems and have been drifting free through the galaxy ever since. They are not bound to anything. They travel in straight lines through the emptiness between stars for periods measured in hundreds of millions of years, and occasionally one of them passes near enough to a star to be noticed. A small number have now been detected entering the inner solar system. They announce themselves by their paths. A body bound to the sun follows a closed orbit and will return. These arrive on open paths, moving too fast to be captured, curving once around the sun and departing on a trajectory that will never bring them back. Their speeds relative to the Sun run to tens of kilometers per second, which is the ordinary drift speed of material in this part of the galaxy. The first confirmed visitor was small and unusually elongated, and it showed no visible tail, which made its composition difficult to establish. The second was an unambiguous comet, with a normal coma and a normal tail, and a chemistry that would not have looked out of place among the Sun's own comets. That difference is informative. It suggests the population is diverse rather than exotic, and that other star systems eject roughly the same kinds of material that ours does. Each of those detections happened only because the object came close enough to the Sun to brighten. And that is the basis for an estimate that is worth delivering carefully, because the number is startling and the confidence in it is low. If the detection rate is representative of the true traffic, then the number density of such objects in this part of the galaxy implies that at any given moment, the volume inside 1 light-year contains something on the order of 100 trillion interstellar bodies larger than about 100 meters across. That would make them more numerous inside our own sphere than the Sun's own comets. That estimate rests on a very small number of detections, and it could be wrong by orders of magnitude in either direction. It should be held loosely. But even the conservative end of the range implies something worth sitting with. The space around us is not the Sun's exclusive property. It is continuously threaded with material from other stars, drifting through, unbound, uncounted, and gone again within years or decades. The Sun has certainly contributed its share to that traffic. During the formation and migration of the giant planets, an enormous mass of icy material was flung out of this system entirely, and it did not stop at the edge. It is out there now, spread through the galaxy, and some of it is presumably passing through other stars' skies as we speak. The exchange runs in both directions, and always has. There is a related point about the medium the sphere is currently moving through, and it is easy to overlook because it is invisible in every sense. The solar system is presently inside a warm, low-density cloud of interstellar gas, some tens of light-years across, which the Sun entered at some point in the last 100,000 years or so, and will leave again in a few tens of thousands more. That cloud is itself sitting inside a far larger and far emptier cavity, several hundred light-years across, carved out of the galaxy by ancient stellar explosions, and still expanding slowly outward. So the local environment is a small, warm pocket inside a large, hot hollow, and the Sun is drifting through both. None of that is stationary relative to us. The cloud moves. The Sun moves. The relative motion is about 26 kilometers per second, which means the sphere is continuously sweeping up new material at the front and leaving old material behind at the back. The gas we are moving through tonight is not the gas we were moving through 100,000 years ago. The dust in that flow is worth a brief note because it is the one component with any real energy. A grain of interstellar dust arriving at 26 kilometers per second carries, per unit of its mass, enough kinetic energy to vaporize itself instantly on contact with anything solid. Individually, they are microscopic and harmless. Collectively, over long enough periods, they are the reason the outer surfaces of anything left in interstellar space are slowly eroded rather than preserved. Alongside the solid traffic, the sphere is flooded with things that pass through everything, including through us. Begin with neutrinos. The Sun produces them as a byproduct of the fusion running in its core at a rate of roughly 200 trillion every second. They travel outward at very nearly the speed of light and interact with matter so weakly that the Sun itself is transparent to them. At any given instant, the number of solar neutrinos in flight inside tonight's sphere is a quantity with more than 40 digits. About 100 trillion of them pass through your body every second. They pass through the bed, through the floor, through the entire thickness of the Earth, and out the other side, and essentially none of them touch anything on the way. Detecting them at all requires enormous instruments, buried deep underground, watching thousands of tons of material and waiting for the occasional interaction. The total number of solar neutrinos ever detected by humanity is a vanishingly small fraction of the number that pass through a single hand in a single second. Then there are cosmic rays. These are atomic nuclei, mostly hydrogen, accelerated to enormous energies by distant stellar explosions and by the shock fronts they leave behind. They arrive from every direction, having wandered through the galaxy's magnetic field for millions of years, and by the time they get here, all information about where they came from has been erased. The sun's magnetic bubble deflects a portion of them. The rest come through. Then there is starlight. Light from every star in this galaxy crosses the sphere constantly, at every moment, in every direction. It is faint, but it is not negligible, and there is an elegant coincidence hidden in it. The energy density of starlight in this part of the galaxy, the energy density of the galactic magnetic field, and the energy density of cosmic rays all come out at roughly the same modest value, about 1 electron volt per cubic centimeter. 3 completely different phenomena, arriving at the same number. It is one of the tidier results in astrophysics, and it is thought to reflect a genuine physical coupling rather than chance. And then there is the sun's own light, which is the largest single flow crossing the sphere and the one easiest to forget. At any instant, tonight's sphere holds about 1 year's worth of sunlight in transit. Every photon the sun has emitted in the past 12 months is still inside the boundary, still traveling outward, still on its way to somewhere. It is a shell of light 1 light-year thick, continuously replenished at the center and continuously leaving at the edge. The total energy in that shell is large by human standards and small by cosmic ones. Converted to mass, it comes to about 100,000 trillion kilograms. That is roughly the mass of a modest asteroid, spread evenly through 3.5 billion trillion cubic kilometers of space. All the sunlight inside 1 light-year of Earth, gathered together, would weigh about as much as a single rock 40 kilometers across. There is one detail about the visiting objects that is easy to get backwards. Passing through the solar system does not slow them down. An unbound body falls inward, gaining speed all the way, whips around the sun, and then climbs back out, losing exactly the speed it gained. It leaves with the same velocity relative to the sun that it arrived with. Nothing is exchanged. The encounter changes the direction of travel and nothing else, which is why none of these objects can ever be captured by an ordinary passage, and why every one that arrives is already leaving. The sun's wind is out there too, though only in the innermost 100 millionth of the volume, and beyond that boundary it merges with the general flow of the galaxy and stops being ours. So the sphere is not still, and it is not sealed. Material from other stars drifts through it continuously. Radiation from every direction crosses it without slowing. The sun's own light fills it, leaves it, and is replaced. It is less a container of objects than a region of constant, silent traffic, most of it passing straight through everything in its path without leaving any record that it was ever here. There is one more accounting to do before the census closes, and it produces the strangest result of the night. So far we have been counting objects. Let us instead count mass and rank the contents of the sphere by weight rather than by number. Start with everything that can be seen or touched. The sun comes to about 333,000 Earth masses. The 8 planets come to about 446. All 300 moons together come to about 1/8 of one. The entire population beyond Neptune, the 100,000 icy bodies and everything below them, comes to about 2/100ths of an Earth mass. The whole asteroid belt comes to 5/10,000ths. And the outer comet cloud, all trillion or more of its members, comes to perhaps 1 to 5 Earth masses, though it may well be less. That is the visible inventory, and after the Sun the ranking is straightforward. The planets dominate, and everything else is a scattering of dust by comparison. Now the things that cannot be photographed. Begin with the interstellar gas, because the arithmetic here is genuinely counterintuitive. The sphere sits inside a warm cloud of interstellar material at a density of roughly 1/5 of an atom per cubic centimeter. That is an almost meaningless amount of matter. It is about 10 million billion times thinner than the air in the room you are in. It is a far better vacuum than any laboratory on Earth has ever produced, and no instrument placed in it would register anything at all as pressure. But the volume is enormous, and enormous volumes convert almost nothing into a great deal. Multiply that density by the volume inside 1 light-year, and the thin hydrogen filling the space around us comes to roughly 200 Earth masses. 200 Earth masses of gas so thin that it is functionally a vacuum. That is somewhere between 40 and 200 times the mass of every comet in the outer cloud combined. The emptiness between the objects outweighs the objects by a large factor, purely because there is so much more of it. There is a further oddity in that gas. Its temperature is around 7,000 Kelvin. That sounds violent, and it means almost nothing. Temperature at that density describes how fast the individual particles are moving, not how much heat is available. A surface placed out there would be struck so rarely that it would radiate away heat far faster than collisions could deliver it, and it would cool rapidly toward the temperature of the cosmic background, regardless of how fast the surrounding particles are traveling. The gas is hot, and the environment is cold, and both statements are true at once. Interstellar dust makes up about 1% of that material by mass, in grains of silicate and carbon, most of them smaller than the wavelength of visible light. 1% of 200 Earth masses is 2 Earth masses of dust inside the sphere. That is comfortably more than everything in the asteroid belt, and probably more than everything beyond Neptune. And then there is the last entry in the census, and it is the one that changes the ranking. The galaxy contains a great deal more mass than can be accounted for by the things that shine. This is not a fringe idea, and it is not a single measurement. It follows from 4 independent lines of evidence that point at the same missing quantity: the way galaxies rotate, with their outer regions moving far faster than the visible mass permits, the motions of galaxies within clusters, which are far too rapid to be bound by what can be seen, the detailed pattern of the earliest light in the universe, which requires a component that does not interact with radiation, and the way mass bends the light of objects behind it, which reveals mass where nothing is visible. Whatever this material is, it is spread through the galaxy in a smooth, thin halo, and it is here as much as it is anywhere. The local density is estimated at around 1/100th of a solar mass per cubic parsec. Convert that to the volume of tonight's sphere, and the answer comes out at something on the order of 400 Earth masses. 400 Earth masses of invisible material inside 1 light-year of Earth, right now, passing through everything without effect. The figure is uncertain by perhaps a factor of 2, and it should be presented with that caveat attached. But even at the low end of the range, it places this invisible component squarely in the same league as every planet in the solar system combined. 400 against 446. They are, as far as anyone can tell, roughly the same quantity. So here is the mass census of the sphere, ranked honestly. First, the Sun, by an enormous margin. Then a near tie between two things, all 8 planets, and an invisible halo that has never been imaged, never been isolated, and never been detected in a laboratory despite decades of dedicated attempts. Then, in third place, a fog of hydrogen so thin it counts as a vacuum, at roughly 200 Earth masses. Then, a long way down, 2 Earth masses of interstellar dust. Then the entire outer comet cloud, at perhaps 1 to 5. And only then, every moon, every asteroid, every catalogued body beyond Neptune, every object that has ever been given a name or a number, all of it together, well below 1 Earth mass. Of the 4 largest constituents of the volume inside 1 light-year of Earth, 3 have never been imaged, and 2 of them cannot be. It is worth being clear about what the invisible halo is and is not, because it is easy to picture wrongly. There is no dark object out there. There is no hidden mass concentrated into a shape. The material does not clump on small scales the way ordinary matter does, precisely because it cannot shed energy by radiating and therefore cannot collapse. It is smooth, thin, and everywhere at once. If the local estimate is correct, roughly a kilogram of it drifts through a room-sized volume every few thousand years, and absolutely nothing happens when it does. It passes through the walls, through the floor, through the planet, and out the other side, exactly as the neutrinos do, only more quietly, because it does not even interact by the weak processes that make neutrinos occasionally detectable. The attempts to catch it directly are worth a moment, because they are among the most patient experiments ever conducted. Detectors are built deep underground, in old mines and beneath mountains, where the rock above filters out the ordinary radiation that would otherwise swamp everything. Inside, cooled to fractions of a degree above absolute zero and shielded from vibration, sit tanks of liquid xenon or crystals of germanium, waiting for a single atomic nucleus to recoil from a collision that may happen a few times a year, or not at all. Some of these experiments have now been running for decades. None has produced a confirmed detection. Each null result narrows the range of possibilities a little further, and the search continues, quietly, without any expectation of a quick answer. It is also worth noting that this is not a local peculiarity. On the largest scales, the ordinary matter that makes up stars and planets and people accounts for only about 5% of the total content of the universe. The invisible component accounts for roughly 27%, and a still stranger component associated with the expansion of space accounts for the remaining 68%. By that accounting, everything we have spent tonight counting, the sun included, belongs to a minority constituent of the cosmos, and the sphere around us reflects the same proportions as everything else. There is a final wrinkle in the gas figure that keeps the picture honest. The material inside the sphere is not uniform in state. Some of it is neutral hydrogen, some is ionized, and the balance shifts across the boundary of the sun's magnetic bubble. Inside the bubble, the sun's own radiation strips electrons from what drifts in. Outside, the ionization is set by the ultraviolet light of distant hot stars. So even the simplest component of the census, the plain hydrogen filling the space, is layered rather than uniform, and the 200 Earth mass figure is an average across a structure with genuine internal variation, which produces a rather beautiful summary of the whole census. Rank the sphere by number, and it is 1 trillion comets. Rank it by mass, and it is a star, then a tie between the planets and something nobody has ever seen. Rank it by volume, and it is almost entirely empty. Rank it by what we have observed, and it is 4 parts in a billion. 4 different questions about the same region of space, and 4 completely different pictures, none of which resembles the diagram in the classroom. The diagram is not wrong, exactly. It simply answers a fifth question, which is where the planets are, and that turns out to be the least representative thing anyone could ask about this volume. Having counted what is present, the census closes with an entry for what is absent, and it is the largest entry of all. Within 1 light-year of Earth, there is no other star. Not one. No yellow star, no red dwarf, no white dwarf, no brown dwarf, no confirmed free-floating planet. There is the Sun, and there is nothing else in the sphere that has ever generated its own light, or ever will. The nearest star system lies at about 4.24 light-years. That is more than 4 times the radius of tonight's sphere, which means it is more than 70 times the volume away. The nearest known pair of brown dwarfs, the faintest and coolest kind of failed star, sits at around 6.5 light-years. Neither is close by any definition that makes the sphere feel crowded. This is a genuinely surprising result for anyone carrying the usual mental picture of the galaxy, in which stars are packed close and the sky is thick with neighbors. In this region, they are not. The Sun sits alone at the center of an enormous volume that contains no other star of any kind, and every object inside that volume, which is gravitationally bound to anything at all, is bound to the Sun. The sphere is, in stellar terms, entirely and exclusively ours. But the arrangement is temporary, and this is where the census stops being a snapshot and becomes something slower and more interesting. Stars are not fixed relative to one another. They move on their own orbits around the center of the galaxy, at slightly different speeds and slightly different inclinations, and the neighborhood is continuously reshuffled. Typical relative speeds run to tens of kilometers per second. On average, some star passes within 1 light-year of the Sun roughly once every million years. Over the Sun's lifetime, that means thousands of such passages have already taken place. 2 are worth describing. A small red star with a brown dwarf companion passed within about 8/10 of a light-year, some 70,000 years ago. That is inside tonight's boundary. It moved through the outer regions of the comet cloud, while modern humans were already alive on this planet, already making tools, already looking up. From the ground, it would have been a faint red point, too dim to attract attention on most nights, though it flares from time to time and might occasionally have brightened enough to be noticed. Nobody who saw it could have known what it was. It passed through the outermost shelves of the solar system, gently disturbed the orbits of some enormous number of comets, and continued on its way. The consequences of that stirring are still arriving. Some of those disturbed orbits are only now beginning to fall inward, and will not reach the inner solar system for millions of years yet. The second is ahead of us, rather than behind. A star currently a little over 60 light-years away is on a path that will bring it within about 17/100ths of a light-year in roughly 1.3 million years. That is around 11,000 astronomical units, which places it deep inside the comet cloud, and it is by a wide margin the closest known future approach of anything. When it arrives, it will be the brightest object in the night sky apart from the moon. It will hang there for many thousands of years, slowly brightening and slowly fading, as ordinary and permanent a feature of the sky as any constellation. And it will pass through the inner comet cloud and scatter a portion of it into new orbits, some of them directed inward. That effect is worth describing accurately rather than dramatically, because it is often overstated. A close stellar passage does not fling a volley of comets at the inner planets. It changes orbits slowly, and the resulting increase in inbound long-period comets is spread over a few million years and is modest in size. It is a gentle, geological adjustment to the outer inventory, not an event. So the sphere is not a stable list. It is a slow, quiet exchange. Comets are lost outward when passing stars strip them away. Material is gained from the galaxy as we sweep through new clouds of gas. Interstellar objects thread through continuously and leave. And roughly once every million years, the neighborhood receives a visitor that rearranges the outermost shelves and then departs. All of this reshuffling happens because the sphere is itself in motion and on a much grander circuit than anything inside it. The Sun carries this entire volume around the center of the galaxy once every 230 million years or so, at about 230 kilometers per second. It has completed roughly 20 such circuits since it formed. The last time the Sun was in this part of its orbit, the first dinosaurs were beginning to appear. Over those 20 circuits, the neighborhood has changed repeatedly. The Sun has passed through the spiral arms, where stars and gas are more densely packed, and through the quieter regions between them. It has almost certainly passed through at least one or two clouds of dense molecular gas, and each such passage would have compressed the bubble of solar wind dramatically, perhaps pushing its boundary inside the orbits of the outer planets. It has drifted above the plane of the galaxy and back down through it, several times over, on a gentle vertical oscillation. None of that left any obvious mark on the inner solar system. The planets kept their orbits. The Earth kept its oceans. But the outer shelves of the sphere, where objects are bound so weakly that a passing star can lift them away, have been rearranged again and again, and the inventory we have counted tonight is the current state of something that has been quietly reorganizing itself for 4.5 billion years. There is a deeper version of this point, and it concerns the beginning rather than the future. The Sun almost certainly did not form alone. Stars form in clusters, out of the collapse of large clouds of gas, and the Sun very likely emerged among hundreds or thousands of siblings, packed together in a region where the average separation between stars was a small fraction of a light year. In that environment, tonight's sphere would have contained not one star, but many. The sky would have been genuinely crowded, with several stars bright enough to cast shadows, and close approaches would have been routine rather than exceptional. Which means the outer comet cloud, as we now understand it, could not have survived in that environment. Objects bound at 60,000 astronomical units are held so weakly that a star passing at a fraction of a light year would strip a great many of them away. The cloud we have counted tonight is not the original one. It is what was assembled and retained after the cluster dispersed, once the Sun had drifted out into open space and the neighborhood had become quiet enough for weakly bound objects to stay put. The siblings themselves are long gone. They spread around the galaxy over hundreds of millions of years and are now scattered through it, indistinguishable from every other star of similar age. A handful of candidates have been proposed on the basis of composition and motion. None has been confirmed, and the search is genuinely difficult, because after 4.5 billion years the orbits have been thoroughly mixed. One further absence is worth recording, because the honest answer is that we do not know. Free-floating planets, worlds ejected from their systems and now drifting through the galaxy without a star, may be common. The statistics are poor, but they permit somewhere between none and about one such object inside a volume the size of tonight's sphere. If one is out there, we would almost certainly not have found it, for exactly the reasons laid out earlier. It would be cold, dark, slow-moving, and utterly undetectable by any current method. So the final entry in the census is an honest blank. There is no other star inside 1 light year of Earth. There may or may not be a starless world. We cannot say, and we will not be able to say for a long time. And there is one last note about the nearest system, 4 light years out, which puts the whole arrangement in perspective. It is not a single star, but 3. Two of them are broadly sun-like, orbiting one another at a distance comparable to the width of our own planetary system. The third is a small red star far out on a very long orbit around the pair, and it happens to be the closest of the three to us at present. It is also, despite being the nearest star to the Sun in the entire galaxy, far too faint to be seen with the unaided eye from anywhere on Earth. The closest star to us is invisible, and has been for the whole of human history, and nobody knew it was there until instruments were built that could find it. The census is finished. It is worth reading the result out once, in full, before we let it settle. Within 1 light-year of Earth, there is one star, holding almost all of the mass. There are 8 planets, amounting to 446 times the weight of this one. There are somewhere over 300 moons, several of them larger than Mercury, and together they do not add up to a fifth of the Earth. There are 1.5 million catalogued asteroids, weighing less than a 20th of the Moon between them. There are more than 100,000 icy bodies beyond Neptune, the surviving 1% of a region that has lost almost everything it once held. There is a shell of comets, containing on the order of 1 trillion objects, sitting at 3 or 4 Kelvin, moving at the speed of a car, taking 16 million years to complete a single orbit, and spaced so widely that each one's nearest neighbor is as far away as Uranus is from the Sun. There is a fog of interstellar hydrogen, weighing about 200 Earths, and so thin that it is a better vacuum than anything we can manufacture. There are perhaps 2 Earth masses of interstellar dust. There is an invisible halo of material, roughly matching every planet in the solar system put together, that has never been isolated, never been photographed, and never once been caught in a detector, despite decades of patient waiting deep underground. And filling all of it, between all of it, around all of it, there is an amount of nothing that no honest description conveys. Of all of that, we have ever detected anything at all in about 4 parts in a billion of the volume. That is the answer to the question, and there is a natural instinct to hear it as a disappointment. It is worth resisting that instinct because the emptiness is not a deprivation. It is the precondition. Consider what a crowded version of this sphere would have meant. If another star sat inside 1 light-year, the outer comet cloud would have been stripped away long ago, and the orbits of the planets themselves would have been slowly disturbed. If the space between were dense rather than nearly empty, the Earth's orbit would have decayed over geological time. If close stellar passages happened every few thousand years rather than every million, the comet flux into the inner system would never have settled into the quiet trickle it is now. The stability that allowed a planet to hold one climate for billions of years, to keep an ocean, to run the same slow chemistry uninterrupted for long enough that something eventually looked up and started counting, is a direct consequence of how empty this sphere is. The Sun is alone inside its own light year, because a sun that was not alone could not have been a home. And the emptiness is what lets us see anything at all. If the space around us were filled, the sky would be closed. We would have no stars, no galaxies, no cosmic background, no way to know that anything existed beyond the atmosphere. Every measurement in this entire census, and every measurement in the history of astronomy, was possible only because there is almost nothing between here and everywhere else. So the correct way to hold tonight's result is not that we have seen almost none of the space around us. It is that the space around us is so quiet, so transparent, and so undisturbed that a small, warm planet has been able to sit at the center of it for 4.5 billion years and slowly work out what is there. Everything we counted is still out there tonight, doing what it has always done. The comets are drifting at walking pace in the dark, 3 degrees above absolute zero, 300 orbits into a journey that began before there was an Earth to orbit around. The reddish worlds on their 11,000-year paths are moving outward, unlit and unwatched, and will not be visible again for longer than there has been recorded history. The invisible halo is drifting through the room, through the bed, through you, without touching anything. The nearest other star is holding its distance, 4 times further away than the boundary we drew, and it will hold it for a very long time. The 5 machines are still going, at 17 kilometers a second, 17,000 years from the edge, carrying instruments that stopped being modern half a century ago and still work. And the sunlight that left the sun this morning is now 150 million kilometers out, on its way to a boundary it will reach next summer, at which point it will keep going, out past the comets, out past the sun's grip, into the long dark between the stars, carrying a faint record of an ordinary day on an ordinary planet, outward forever. None of it needs anything from us. None of it is waiting, and none of it has ever registered that it was counted at all. It has been arranged this way since long before there was anyone to describe it, and it will stay arranged this way long after. It is also worth saying, gently, that the ledger is not closed. It will not change dramatically because the 4th power dimming law is not negotiable and no instrument will ever overcome a factor of 200 billion. But it will change at the edges, and the changes will be quiet ones. New survey telescopes are beginning to photograph the entire visible sky every few nights, building a record of everything that moves, and they will find outer objects at a rate nobody has managed before. Most of them will be ordinary members of populations we already understand. A few will not be. If a distant massive body exists, this is roughly the era in which it would be found or ruled out. The occultation work will continue too, patiently, watching background stars for the fraction of a second flicker of something unseen passing in front of them. It is an unglamorous method, and it produces almost no information per detection. But it is the only tool that reaches into the outer sphere at all, and given enough years and enough stars, it will eventually put a real number on how many kilometer-scale bodies are out there. And every century or so, on average, a long-period comet will fall in from the outer cloud on its first approach in millions of years, carrying ices that have never been warmed, and for a few months, a small piece of that unseen population will be visible from the ground. Those are the only samples the cloud will ever send us, and it has been sending them steadily, without interruption, since long before anyone was here to notice. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. One star, a handful of worlds, a trillion frozen bodies moving at the speed of a slow car, and an immensity of quiet that has no comparison in ordinary experience. Almost none of it has ever been seen. Almost none of it ever will be. And it is in no hurry whatsoever. Let your shoulders soften. Let the long, cold, patient distances hold their positions without you. Sleep well, and good night.